Hello, hi guys. Can you hear me? Just write down in the chat if you can hear me and also if you can see my screen. Hello, hi. Is my voice clearly audible? I guess yes. Okay, so okay. How was the contest? How many problems were you able to solve? You may write in the chat. Hmm, Okay. Okay, for those who are saying contest was bad, so that's just part of it. Sometimes it goes good, sometimes it goes bad, so no need to worry about that. Okay, so I guess we can start with the discussion for today. We'll be discussing 5 problems up till E. About B, I don't know the rating. Probably about 1200, maybe, or I'm not sure. Yeah, B was a slightly good problem, you may say, compared to A, which was just way too easy. Okay. Okay, so I think we can start with the discussion. Okay, so hello guys, I am Abhinav and this is TLE Eliminators. So welcome to the post-contest discussion of the Codeforces Educational Round 177. Okay, so before starting with the discussion, let me just tell you briefly about the newly launched second version of the CP31 sheet. So for all those who are not aware, in this sheet you would get 31 hand-picked problems from each rating from 800 up till 1900, and for each problems teaches you a unique idea, as well as in the new interface of the seat you can see that you have various features, like you can connect your code forces handle and it would automatically sync your progress from your account. Also there's a leaderboard where you can compete with your friend of who solves more problems. There's a dedicated discussion session section for each problem, etc. So uh, as well as every week it's 7 to 8 video solutions of the seats are being released in the TLE Eliminators channel, so do check them out. The link to the seat will be in the description. Okay, so let's start with the PCD now. So we'll discuss the first 5 problems of the contest. So let's start with the first problem, which is Cloudberry Jam. So the most valuable berry of, okay, whatever the story is, basically the problem is just you need to take equal amounts of berries and sugar to cook them. So if you have 2 kg of berry and 2 kg of sugar, you can combine them to cook 3 kg of jam. Okay, so they combined 2 kg plus 2 kg would be 4 kg, but after cooking that it get reduced to 3 kg. So basically 25% gets evaporated after cooking. So with 2 kg berries and 2 kgs of sugar, you can create a 1 3 kilogram jar. So you need to find how much would you need to create n 3 kilogram jars. That's the problem. So basically for every test case you just need to find how many kilograms of cloudberries do you need to create n 3 kilogram jar. So to create 1 3 kilogram jar you would need 2 kg of berries, 2 kg of sugar. So to create n 3 kilogram jars you would need 2 kg for each, basically 2 kg of berries. So cloudberries and berries, I think it's the same thing. There's just above it's written berries, but it means the same. Okay, so for each test case just you need to output the amount of berries needed for the jam in kilograms. So for each test case, if n is 1, just output 2n. Answer is 2. For n equal to 3, output 6. So the problem was just this simple. For given input n, you need to just output 2n. So I hope it's clear. I can directly move to the code. Just input n and output 2n. That's all that you need to do. Just take all the t test cases. For each test case, input n, output 2n. Time complexity would be obviously order of 1. Space complexity would also be order of 1. Okay. I hope this problem is clear. There's no doubt in this problem. It was just about understanding the problem statement. Code was nothing. So I think we can move on to the B problem now. Okay. Okay. So problem B. There's an array A consisting of n positive integers and a positive integer k. An array B is created from array A according to the following rules. Okay, so you are given an array A with n positive integers, and from that array A, you are going to create an array B. How do you create that? So the size of array B would be n into k. What would be the n into k numbers in that? The first n numbers are the same as they are in array A, that is bi equal to ai. After that, for any I greater than n, bi is bi minus n. Okay, so if you have array A, the first four numbers are the same, 2, 3, 1, 4. After that, just keep copying that again and again. So b5 would be equal to b5 minus n, that is b1. So 2 would come here. b6 would be b2. So 3 would come here. b7 would be b3. So basically copy that same array A k times. So here k was 3. So just copy that array A 3 times. That's what the array B is. So now in this array B, you need to find that you are given a number x. It is required to count the number of such positions L for which there exists a position R greater than L such that the sum of elements of array B on the segment L to R is at least x. Okay, so in other words, basically, you need to find for any L, can you get a subarray starting from L so that its sum is from L to R, the sum of the subarray is at least x. Okay, so you would be given x in the input and you need to find how many such valid L exist that satisfies this condition in the array B. Okay, so you are given array A and n and k. So through n, k and array A, you can create array B. In that array B, you are given x, find how many such L exist. Okay, that's the problem. I hope by reading the problem statement, this is clear. Now, let's take this test case and understand more clearly what you need to do. Okay, so let's say you have this test case. So in this test case, you have n, k, and x, and this is your array A. So first of all, through this array A, you are going to create this array, the array B. Array B is just k copies of array A written side by side. So k is 3, so just write 3 copies of array A. So 3, 4, 2, 1, 5. Okay, first copy, then again copy this same thing another time. So again 3, 4, 2, 1, 5. Okay, now again copy this one more time. So 3, 4, 2, 1, 5. Okay, so you have copied this array A 3 times. This is your array B. Okay, now in this array B, you need to search how many such L exist so that it satisfies the condition that there is a subarray from L to R such that the sum of the subarray is greater than equal to X. Okay, so you need to find, let's suppose you are taking this L. So if there is any even one such R which satisfies the condition that the sum from L to R, this sum is greater than equal to X, then you would say that this L is valid. Okay, now take any other L. If there is any one R, okay, for this L maybe there would be a different R. Let's say this R is going to satisfy that the sum of the array is greater than equal to X. You would say yes, this L is valid. Now you need to just count the number of such valid L. That's your final answer. So for this particular test case, you needed to have X equal to 10. So if you try to take this L, then you may maybe sum up, let's say sum till here. 3 plus 4, 7 plus 2, 9 plus 1, 10 plus 15. Okay, 15 obviously greater than 10. So there is such valid R for which it's okay. Like for these starting values, obviously you can even pick an R. Like if you just understand the condition that for any L you need to pick a R so that the sum is greater than equal to X. So basically you need to maximize your sum, and you know the values in the array are all positive numbers, they are no negative numbers. So if the values are not negative, why would you ever pick a R in the middle? Always pick the last R, always pick the whole suffix. Why do you need to cut it when you can maximize it? It doesn't affect your answer. Basically you need to maximize your sum of the subarray so that it exceeds X. So the first basic conclusion is always pick a R, the last index, always pick the last index as your R. So basically for each index you need to just check if the suffix sum of till that index, if that suffix sum is greater than equal to X. If that suffix sum is greater than equal to X, then that L is valid. Okay, so for the starting values, when the sum is very big, it would always be greater than equal to X. So if you are taking 10, this would be greater than equal to 10, this would be greater than equal to 10. Okay, so these all would be greater than equal to 10. When would it be not greater than equal to 10? If you need to search, like for this particular array, if you take this sum, 3 plus 4, 7 plus 2, 9, 10, 15, this would be 15 greater than equal to 10. Okay, so this is valid. Now let's take this sum. This sum is 4, 2, 6, 1, 7 and 5, 12. So this 12 is also greater than equal to 10. So this is also valid. Let's take this sum. So 2 plus 1, 3 and 5, 8. So this 8 is less than 10. So this would be invalid. So if this is invalid, this would also be invalid because 6 is less than 10. This would be invalid because 5 is less than 10. Okay. So all these 3 L would be invalid. For these L, you cannot select a R so that the sum is greater than equal to X. But the rest, all of the L would be valid. So how many valid L exist in this? In total, there are 5 into 3, 15. Size of the array is 15. Out of them, 3 are invalid. So there are 12 valid L in this array. So for this test case, your answer would be, for the first test case, 12. Okay, so I hope the test case is also clear and the logic of the problem would also be almost clear to you. So what the logic of the problem is now? So for the array B, you just basically you have to take the suffix from the right side, just keep adding until the suffix sum is less than X. Okay, these are invalid. After a certain point you would reach that yes, this sum becomes greater than equal to X. So then this would become valid, and after that all of them would be valid. So you just need to search for this one particular point. Before that point all are invalid, and after that point all are valid. So brute force approach would be from the right side, just start taking the suffix sum until you get to a point where your sum exceeds X. Then you would get that point. So once you get that point, you can just subtract this, whatever the length of this is, from the total length of n into k. That would be your answer. But if you do the brute force approach, the length of this array B can be n into k. So in worst case, you may have to search. So your time complexity would be order of n into k. And you can see that constraints are n and k both are 1e5. So this n into k would be 10 to the power 10. This would obviously give you a TLE. Okay. So you need to optimize this thing to, instead of order of n into k, you need to optimize it further to somewhat of order of n. So how do you do that? Basically, you need to observe that this, what is this array B? This array B is actually array A taken many times. So you have to take this array A k number of times. Now, where would you find that particular point after which your suffix sum exceeds. So either, like, what would happen here? You have the array A k times. Okay, like let's generalize it. Your array B is actually array A 1 time, 2 time, 3 time. So k times. So this is the first, second, third, and kth array A. So this is your array A, array A, array A, array A. Now in this array B, you need to search for a point so that this suffix sum just exceeds x. Okay, so one way is, if you look like, if you take the sum of this array A, what would be like if you start taking the sum from the right side? Okay, this particular array A would have some sum. Let's say the sum of array A is S. Okay, S is the sum of array A. So this much sum would be S, this much sum would be S, this much sum would be S. Same way from the right side, this much sum would be S, the k minus 1th array A, that would be S. Okay, so like if I'm saying this here is your kth array A, this is your k minus 1th array A, k minus 2th array A, and after that dot dot dot, this is your first array A. So if I am telling that if your x, the given x is less than or equal to S, the first thing is, if this is less than your sum, then in your last array A, only searching in the last array A, you will find that point until where you have invalid else. But if this x is greater than S, then in that case, you would basically cover this complete last array. That would give you a sum of S. And then in the second last array, if that x is greater than 2S, then this whole last second array would also be taken. If x is greater than 3S, then the last three arrays would be taken completely. So how many complete arrays would be taken from the end? So that would be whatever x you have, x divided by S, whatever is the integer division of that. Okay, I'll say whatever is the floor of x divided by S, this would be the number of complete like arrays from end that would be invalid. Okay, the indexes of whom would be invalid. So whatever is the integer division of x by S, that many you would obviously have. After that, whatever is the remainder, so whatever is the remainder of x modulo S, those would be the number of those who, that would be the amount that you need to search, like after skipping this many arrays. So let's say this value is 3, so you would skip 3 arrays. After that, in the last fourth array, you would search for this sum. Okay, so from here, after how much you would get this sum. So this you can calculate in order of 1. So how many arrays you need to skip, and then you would get one particular array where you need to search, so that in that you can do a linear search in order of n only. Okay, so this way we can optimize it to order of n. This was one approach. Another approach is, obviously you can see that it's 1 1 1 1 and 0 0 0. This is a predicate function, you can see. So you can also apply binary search on answer in this particular problem. So another approach would be apply binary search on answer and assume whatever is your mid, that is this particular point. Like you need to search for this particular point, the lowest point where your answer is invalid, and then you just need to create a check function to check whether that L is valid or invalid. Now in order to check, what you can do is, whatever index you have, just check that that index belongs to which array. Okay, so after that index, how many complete arrays are there? So if after that index, whatever is the number of complete arrays, S into that would be the sum of those, and in whichever array that index belongs, you take the suffix sum of that array. So pre-compute the suffix sum, and just by dividing that index by n, you can get in which particular array it belongs. So that way you can create your check function inside the binary search and search inside the binary search. After pre-computing your suffix sum, you can do it in order of 1 also. So overall suffix sum would be n and binary search would be log n. So n plus log n in that time you can do using a binary search. Okay, so that is one approach, but the code that I'm going to show would be about this approach without binary search, just in order of n how you can do. So that's quite simple. This is the number of complete arrays from the n that you are going to skip, and this is the suffix sum that you would be you are going to search for. Okay, so I hope like both the approaches are clear. I'll show the code for this approach. Maybe you can try the binary search approach by yourself. Okay, is there any doubt in the approach? Then you may ask. Yeah, like prefix sum in the reverse of the array you say, or you say the suffix sum, both mean the same thing. Okay, so I think the approach is clear. We can move on to the code to understand better what exactly we are doing. So one thing like you need to notice here is, okay, like let's take this example here. Let's take in this example only, instead of x is equal to 10, let's say I am giving you x is equal to 20. Okay, so what is the sum of the array? Your sum would be 3 plus 4 7 9 10 15. Your sum is 15. Okay, so first of all, if you have x is equal to 20 here, so you would just search how many complete array sums would we have in 20. So 20 divided by 15, the floor division would give you 1. So there would be one complete array which would sum up to 15 that you are obviously going to skip. So n indexes there are obviously going to get skipped. After that, from here you need to start searching in this particular array till which index do we get a sum of 20 modulo 15 is 5. Okay, so you need to search for a sum of 5. So in this first index, if you see here only, if you start, then you would get a sum of 5. So basically if you start from here, this is valid. So this particular index is valid and all these are invalid. Okay, let's say if x was 21 here, okay, then this 21 modulo 15 would have been 6, and same 21 by 15 would remain 1. So one complete array skipped, and you would start searching from here for 6. So first you would check this suffix sum. So this 5 is less than 6, so you would mark across here and then move ahead. Then you would check this suffix sum. This is 6, okay, which is greater than equal to your x, which is 6. So this you would mark as a tick, that from here all the arrays are valid. So this way you can count the number of invalid arrays as this thing is actually your x divided by s, floor division of that. This multiplied by n would give you the number of invalid states from the end, and subtract this much and how many you got here. So here you got a plus 1 extra. So subtract this much from n into k. Okay, so here n into k was 5 into 3 equal to 15. From that you would subtract, this was 1 into 5 plus 1 6. So 15 minus 6 was 9. Okay, I hope that dry run is also clear and how you are getting to the answer. Now one small edge case was here that I'll just explain quickly before moving to the code is, let's say you take x is equal to 15 in this problem. So when the x is exactly equal to s or a multiple of s, that means you are skipping. Okay, so then you would say that for this particular case, let's say x is 15, or let's take x is equal to 30 here. Let's take x is equal to 30 here. Then what you would say, that you would say x by s is 30 by 15. The floor division is 2. So basically you would skip 2 complete arrays you would say that you would skip 2 complete arrays. Okay, so you would basically skip 2 into n, which is 2 into 5, 10 positions. After that, you would start searching for x modulo s, which is 0 here. So from here, you would start searching for 0. So obviously, the first value would only become valid. But here, if you see, I'm telling that this state is invalid. But if you take the suffix sum from here, then this total sum is 15 plus 15 equal to 30. And this 30 is greater than equal to 30. It is greater than equal to x. So this particular state is not valid. This particular state is not invalid. It is valid. This particular state is valid. After that, all the states are invalid. So for that case, what I'm doing is, when it's exactly divisible by s, then instead of taking this quotient as 2, like I'm taking this as 1, I'm skipping just one complete array. Okay, so whenever I get x modulo s as 0, I just skip one complete array and search for the sum of s in this. So it would make the same thing. So just reduce your quotient by 1 and increase your remainder to from 0 to s. Okay, so that way you can handle that case, or maybe you can handle it separately also, no issues. Okay, so that's what I'm doing in the code. I take the sum of the complete array. So this was the input part. After that, I take the sum of the complete array. Okay, one more edge case. If that, what is the total sum of this complete array b? So s is the sum of one array a, and there are k times this array. So k into s is the total sum of array b. If this x exceeds k into s, that means all the positions are invalid. Whatever L you take, even if you take the complete array, you are not going to get a sum of x. So for that, your answer would be 0. You return out. That edge case is handled. Now in xm, I take the remainder of x modulo s, and in q, I take the quotient of x divided by s, the integer division. Now when the remainder is 0, I just decrement the quotient and increment the remainder to s. Okay, in order to handle that particular edge case. Okay, so this I am doing to handle that particular edge case when my x is exactly divisible by s. You can write it separately also in order to handle it if you wish. Okay, after that, my answer is simple. N into k is the total sum that I should have got. From that, I would subtract these invalid states, whatever is the quotient x by s. That many complete arrays, in every complete array, you are skipping n indices. So q into n is the number of indices I am skipping through complete arrays. And then through that suffix sum array in the remainder, what I'm skipping, that I'm calculating through a loop. I start with a suffix sum of 0, and then from the end, I'm running the loop. Sum plus is equal to ai. If that suffix sum exceeds my x remainder, then I break out. Otherwise, I just decrement my answer until that suffix sum is less than my x. So till the suffix sum is less, I keep decrementing my answer. Once it exceeds, I just break out of the loop, and that's my final answer. Okay, so I hope this code is also clear to you. Is there any doubts in this, or should we move to the next problem? Okay. If we analyze the time complexity, this accumulate function is taking order of n time to calculate the sum. This is order of 1. These are all order of 1, order of 1. This for loop is running at max n times. So overall time complexity is order of n. Overall space complexity would be, you are just using an array of size n. All of these are normal variables. So order of n. Okay. I hope this problem is clear, and we can move on to the next problem. Okay, so let's move to the next problem, which is problem C. So in problem C, you are given a permutation of integers from 1 to n in an array of size n, where each integer from 1 to n appears exactly 1. So you are given a permutation basically. You have to process n queries. During the ith query, you have to replace p of di with 0. Each element is replaced with 0 exactly once. The changes made in the queries are saved. After that, that is after the ith query, all the integers are zeros. So basically in each query, you just select any index and change the value at that index to 0. That's what each query is. And then after the query is made, you need to find this value. Find the minimum number of operations required to fix the array, that is transform the current array into any permutation. So initially the array was a permutation, but after each query you are basically removing one value and changing it to 0. So that permutation is disturbed. Now you need to find after each query how many minimum number of operations would be needed to again get back to a permutation. Now that permutation may be equal to the original permutation or a different permutation, but you should just get back to a permutation again. Now what are the operation that you can perform? The operation is select an integer I from 1 to n, replace the ith element of the array with I. So basically you have to replace pi with I. So it may happen that your ith index is changed to 0, you may replace it back to I. But if it was something other than I, then you cannot replace it with something other than I, you have to replace it with pi only. So you would have to do these changes to some other values as well in order to get back your permutation. So that's what the operation is. Now, the answer for each query is calculated independently. So for calculating the array, you just need to compute the minimum number of operations needed to fix it. You don't have to actually fix it. So just compute the number of operations needed and then leave the array as it is, move to the next query. Don't change the array. You don't have to perform the operations, just compute the minimum number of operations required. So I hope the problem statement is clear. If you just quickly look at one of the test case, let's look at this second test case to understand better what we need to do. Okay, so this is your array A and these are your array D. So these are basically your queries. Okay, so these are your queries and this is your array A. So, or your permutation P, not your array A, this is your permutation P. So your permutation is 4, 5, 3, 1, 2. Okay, if I index it, so this is your initial permutation. Now after every query you need to answer. So first query is for index 4. So you need to replace the value at index 4 with 0. So after the first query, this 1 would get replaced with 0. Now you need to answer in this query that for this particular permutation, how many operations would be needed to reduce to again get a permutation from 1 to n out of it. Okay, so here in this given array, this is not a permutation because you have 0, 2, 3, 5, 4. You don't have a 1 and you have a 0 which should not be there. You need to have everything from 1 to up till n, then only it would be a permutation. You cannot have a 0 here and you should not leave anything from 1 to n for it to be a permutation. So how do you change it to permutation? The operations allowed are select any index I and change the value to I. So change any pi to I. That's what the operation is. So change any pi to I. That's what the operation you can perform. You need to find the minimum number of operations to get back. So for this particular case, if you analyze how many operations would be needed, here this is the 0. So definitely this 0 need to be removed. So only option to remove it is perform an operation here. After performing an operation, the index is 4, so it would be replaced by 4. Now you have two 4s here. So again, this is not a permutation. So you need to get rid of one of the 4s. So here if you perform the permutation, it would remain 4. Like perform the operation, it would remain 4. So you cannot perform an operation here. Maybe try performing an operation here. So here if you perform an operation, you will get back to 1. You will get a 1 here because the index is 1. Now if you look at this array, 1, 5, 3, 4, 2, this is a permutation. You have all the values from 1, 2, 3, 4, 5, from 1 to n, all values one time. So this is a permutation. So you have fixed it using two operations, one on 4 and one operation on I equal to 1. So you required two operations to fix it. So answer for this query would be 2. Let's move to the second query. Now just forget what you did here in order to fix and get back to the array you had after the first query. So after the first query, this value at this index was replaced with 0. Now perform the second query. So replace the value at fifth index with 0. So this would get replaced with 0. Now in this particular array, how many operations are needed to get back to a permutation? For this case, you would have to perform an operation here, replace it with 4, perform an operation here, replace it with 1, perform an operation here, replace with 5, perform an operation here, replace with 2. So after performing 4 operations in these indexes, you would get 1, 2, 3, 4, 5. So this is a permutation. So for this test case, your answer was 4. So likewise, you can compute. So for the first two test cases, you can see answer was 2, 4. Likewise, you would get 4 and 5, 5 for the further test cases, further queries. So I hope the problem statement is clear what you need to do. So how do you optimally compute this thing? That what is the minimum operations needed? So in order to understand it, let's try to look at the operation and some properties of a permutation. Let's try to analyze what a permutation is. So if you look at any random, what you need to find in any of the query, that you have some random permutation, and in this permutation, or let's take it, let's take up, let's say n is 6. Okay, you are given this permutation, and then after some queries, let's say this got erased to 0, this 6 got erased to 0. Okay, this 2 got erased to 0, 6 got erased to 0. Okay, so initially you had this. After some of the queries, let's say 2 of the values got replaced to 0. Now how many operations would be needed to fix it? So first of all, let's understand how would you fix. Before getting to the next query, let's say only this 2 is replaced by 0. You have a single 0. Now at minimum, how many operations would be needed? First thing is, obviously here wherever you have a 0, that there obviously you would perform one operation, because you don't want to have a 0. So the only way to get rid of this 0 is perform an operation here. So obviously you would perform an operation here. First thing is, you would perform an operation on every 0. Now would you ever perform an operation on one particular index 2 times? Answer is no, obviously, because if you perform an operation on this 3, it would replace it with 3. Again performing it on 3 means nothing. 3 get replaced by 3. So on any one particular index I, you would perform an operation one time only. So your final answer is just the set of indices where you would perform an operation. So basically you need to find those set of indices where if you perform an operation and replace that pi with I, then after that the overall array becomes a permutation. So here if you see, you could like, if you look at this array, this is like interdependent, because if you replace this 0, if you perform an operation and replace this with a 3, now you have two 3s. So obviously you would perform an operation here. The only way to get rid of a 3 is perform an operation here. So you would definitely perform an operation here. So you would perform an operation here, replace it with 2. Now once you replace it with 2, this 3 2 got exchanged. So your basically work is done. Once this got replaced with 2, you have a permutation. Okay, let's suppose instead of 3 2, I had 3 and 1 here. Okay, now what would happen? So here you would have to perform an operation to replace it with 3. Now once you replaced it with 3 after performing this operation, you have two 3s. So definitely you need to get rid of one of the 3s. So you would perform an operation here for sure. Once you perform an operation here, it get replaced by 1. Now after this get replaced, you have two 1s. So again, this is still not a permutation, because you have 2 times 1. So you need to get rid of at least one of the 1s. So to get rid of, you cannot get rid of this one, because performing an operation here would not mean anything. doing an operation one more time. So you would get rid of this one. So you would have to definitely perform an operation here. So after performing an operation, this gets replaced by 2. And now if you see that after this get replaced by 2, 2 was the missing number in the given array. So now that is found. So this becomes a permutation. So if you look, each element is cyclical, like each element is dependent on another element, because if you perform an operation here, like if this is get replaced by 0, then here you have a value 2. So wherever you have a value 2 at index 3, so wherever you have a value 3, it depends on that value. Okay, so like you can create, like you can mark an arrow here. Whenever you would perform an operation here, you would then have to perform an operation here. Same way, if you look here, if you have a value 3 at index 1, then wherever there is a 1, you would say this is connected like this. Wherever you have a 1, this is connected like this. So whenever you perform an operation here, you would have to perform an operation here as well. Otherwise, like if you don't, you would get 2 ones. Or if that has been replaced by 0, then you obviously have to perform an operation here. So either way, if that value is replaced or not replaced, if you are performing an operation here, you would have to perform here. If you are performing an operation here, you would have to perform here. Now if you look at this value by the same relation, you have a 1, then where in like at index 2 you have a 1, so where do you have the value 2? Here you have a value 2. So you can say that these two are connected. So whenever you perform an operation here, you should have performed an operation here, or you should perform an operation here as well. By this relation, you can say. So now what you can see here, you have a cyclic relation. Okay, this forms a cycle. This 2 is dependent on this index. This 3 is dependent on this 1, and this 1 is dependent on this 2. So whenever you perform an operation on any one of them, you would have to perform an operation on all 3 of them. That's the thing that I want to say. And this, if you like recognize, if you have solved enough problems related to these permutation kind of problems, then you can notice this thing very quickly, that whenever you have a permutation, so like I'll tell this basically, like you can assume this a property of permutation, or this is a very frequently used concept in many problems, that whenever you have a permutation, like here I showed you, you had this permutation. If you look at any permutation, that permutation would be a group of cycles. So if you relate through the indexes, okay, so just take the first value, it's at index 1, so point to index 1, so mark an arrow here. Now here you have index 2, so point wherever you have value 2. Here you have 3, point wherever you have value 3. Now at this index 4, where you have 4, you have 4 here only, so like this is dependent on itself. Now about this, for value 6, there is index 5, where do you have 5? Here you have 5. For 5, you have index 6, where you have 6? Here you have 6. So if you look at this permutation, this is cyclically dependent, this is cyclically dependent on itself, and these two are inter dependent. So if you take any permutation and try to find cycles, you would find some cycle, 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 cycle. Basically any permutation is a group of cycles. Okay, so just take any random permutation. Let's say this time you are taking 3, 4, 5, 1, 2, 7, 6, 8, 9. Let's say for n equal to 9, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's try to draw cyclic dependencies here. You would notice, where is 1? Here we have 1. Where is 2? Here we have 2. Where is 5? Where is 3? Sorry, where is 3? Here we have 3. Where is 1? Sorry, where is 4? Here we have 4. Where is 5, here we have 5. Where is 6? Here we have 6. Where is 7? Here we have 7. Where is 8? Here we have 8. Where is 9? Here we have 9. So if you again look at this, then from this 3, where are you? You move to 1. From 1, you move to 4. From 4, you move to 2. From 2, you move to 5. From 5, you move to 3. So you can see this again forms a cycle. If you arrange it, these all 5 values are interdependent in a cycle. From wherever you start, you reach 2, then 5, then 3, then 1, then 4, then 2, 5, 3, 1, 4. So you have a cycle like this. So these 5 values form a group of cycles. These 2 values, again, you can see it is a cycle. This is a cycle in itself, a cycle in itself. So basically, every permutation is actually a group of cyclic dependencies. So if you know about this, then this problem was quite simple. For every query, just analyze. Now in this, whatever permutation you are given, after some queries, some of the values would be replaced by 0. Now whichever value is replaced by 0, just see to which group it belongs. Okay, now this value belongs to this group, so you would perform an operation all the 3 values of this group. Okay, so 3 operations here. This value belongs to this group, so you perform an operation on both of these values. So 2 operations here. So 3 plus 2, 5 operations would be needed. Now maybe both of these are replaced by 0. So if you look, this belongs to this group, this also belongs to this group. So although there are 2 zeros, but performing an operation on all the 3 values would make it a permutation. You would have 1, 2, you would get back 1, 2, 3. This a different cycle would be replaced by a different 1, 2, 3 would be self cycles. So you would get a permutation. So basically, you need to find among the indices where you have the zeros, which are the different groups that those zeros are covering. The sum of the sizes of those groups would be your answer. Okay, I hope this logic is clear to you. If it is clear, just or it's any doubt is there, you may write. You may apply DSU to group them, but there's obviously an easier way to, if you can just find, like I'll show you the implementation. You don't need DS, actually you don't need DSU to implement this. What you would need to do, just start from any index, keep on moving to the next value, next value, next value until you get back here. So you would get the cycle, mark all the values in the first cycle as 1. Let's say they belong to group 1, so you would mark them in group 1. Okay, then move to the next value which is still unmarked. Okay, you until you get back to the same index, keep performing. So here you got only 1 value, so mark this as group 2. So this belongs to group 2. Now start from this value, keep moving until you get back. Now all the values that you travel through, mark them as group 3. So this way you divided these values into group 1, 2, 3. After that, just run another loop to compute the sizes of each group. Okay, so here in one vector, the group number, you would mark that at index 1 you have group 1, index 2 also group 1. So these 3 values would be marked 1, 1, 1. This would be marked 2, this would be marked 3, 3. You get the group number, run another loop to get the group sizes. So you would say the size of group number 1 is 3, the size of group number 2 is 1, the size of group number 3 is 2. You got the sizes of the groups. After that, in every query, after every query, whichever index you got, whatever is the group of that index, just create another boolean variable to check whether that group is marked 0 or not. Okay, so the first time when that group gets marked 0, add the size of the group to your answer. Okay, so in the first query, if this is marked as 0, add the size of group 1 to your answer, plus 3 to your answer. Again, if this get marked 0, then this group is already added, so you don't add a plus 3. Now if in the next query this group becomes 0, add your group 3, the size of group 3 to your answer. That way you can compute each query in order of 1 only, once you have pre-computed the group numbers and the group sizes. once you have pre-computed these two things, then just maintain a boolean check whether that group number is marked or not marked, and you maintain your answer variable where you would compute your answer, the sum of sizes of the marked groups. Okay, this is about the implementation details. If it is clear, I think we can move to the code now. ठीक है, let's move to the code. So you take the input. After that, you in this group number, you are going to compute the group number of every index initially marked with -1. I run a for loop. If this is still unmarked, like if this is already marked, you continue. If it is unmarked, I initialize a variable k with 1. So group number of the ith index is 1. Initialize another variable with pi until this j becomes equal to I. Keep doing j equal to pi. So you keep moving to the next value. And while moving to the next value, whichever j you go through, mark all of them as the group number of them as k. And then do k plus plus. So the next time when you mark next group, its value would be 2, 3, likewise, the next group number count. So this way you are going to compute the group number of every index, then compute the size of every group number. So size, run through all the values, initialize the size with 0, size of group I plus plus. This way you get the size of every group, and take a boolean check for all the k groups, initialize with false, that initially none of the groups are 0. Initial answer is 0. In every query, you input D. You would check if that group D is already marked. If it is unmarked, add the size of group to your answer and mark it. Okay. So that way you compute your answer and then print your answer. For every query, you would print your answer, kindly have access in. Okay, so I hope the code is also clear. Then we can move to the next problem. Okay, even if you analyze the time complexity, then this was just the input part, and for this part you are running a while loop inside a for loop, but you are marking a group in every time. So whenever if this gets marked, then when you come to the for loop, you would run a continue. So at max you would mark here and run a continue here. So at max for every index, this would run order of n times only. So this is overall order of n only. This for loop is taking order of n time. This again, you have n queries. Every query is order of 1 only. So this is again order of n. Overall time complexity would be order of n. And if you look at the space complexity, then you have a few arrays of size n. This array of size n, k would be at max n. So this also you can assume size n. So it would be order of n only. Okay. So I think we can move on to the next problem now. Okay. So the next is problem problem D, which is even string. So you would like to construct a string S consisting of lowercase Latin letters such that the following condition holds. For every pair of indices I and j such that Si is equal to Sj, the difference of these indices is even, that is I minus j mod 2 equal to 0. Okay, so what this is saying, you are given a string S and you would say that like this is a valid string only if for any pair of index I and j, if the two values are the same, the value at the ith index and the jth index have the same character, then their difference mod 2 should be 0. Basically, they should differ by a even difference. Okay, so their distance should be even. Now you need to construct any string. Constructing a string is too easy, so you will be given an array C of 26 numbers. The required number of occurrences of each individual letter in string S. So you are given an array C of 26 numbers. So every index denotes the frequency of every character. So you have 26 characters in the English alphabet, Latin alphabet. So from A to Z, for every character, you are given the frequency of that character, how many times that character should occur. Your task is to count the number of distinct string S that satisfies all these conditions. You need to form that string S having the frequencies should satisfy this array C, and that string should satisfy this condition. So how many such distinct strings you can form which satisfies these two conditions? You need to output that modulo this value. Okay, so if you analyze the first test case, let's see. So here you are given this array of size 26. What does it denote? It denotes that for character A, B, C, D, E, F, G, H, I, J, K, L, likewise up till Z. For every character, you are given the frequency. So basically, you should have a string S containing two A's, one B, and one K. So it can have two A's and a B and a K. So you need to rearrange these characters to form different strings that satisfies your condition that, let's say you take this string only. Let's check whether it satisfies the given condition. So the given condition is, if you index it, then for any two indexes having the same value. Here, which are the two indices having the same values? Only these two. Like, oh, the A is the only character which is occurring two times. Rest all are occurring one time. So you cannot have two indices having two B's. Okay. So two different indices having A's. These are the only two, only one occurrence of that which you need to check. So for this, if this is the I, this is the J, then J minus I mod is 2 minus 1 mod, which is 1, which is odd. So this string is invalid. Now let's try something different. If I try this string, then here you can say you need to check these two indices. So I is 1, J is 3. So 3 minus 1 mod would be 2. This is even. So you would say that this particular array is valid. This particular string is valid. So how many such valid string exist? For this case, you can see the valid strings would be, this would be one valid string, or you can have, you can't have like this. Yes, you can have A, C, A, B, or you can have B, A, C, A, and C, A, B, A. Okay. So I think these are the four strings that are valid for this particular test case, because only condition here is to check the distance between the A's. So either you would place A's at 1 and 3, or you would place A's at 2 and 4. So when you place at 1 and 3, then either you would have BC or CB, so these two combinations. And when you place at 2, 4, either you would have BC or CB, these two combinations. These are the only four valid combination for this particular test case. And you can see your answer was 4 here. Okay. So I hope the problem statement is clear what you need to do. Now, how do you solve this problem? So the given input, if you see about the constraints, you are given 26 letters, and the sum, like every frequency is at max 5e5, and the sum of CI over all test cases is also 5e5. So whatever is the sum of all these 26 values is basically your size of the string. What is the sum of all the CI? That is your size of the string. Let's say I'm telling this as n. Here the sum was 4. So you would always form a string of size 4. So it is said that this n, the sum of the sizes, basically the size of the string that you are trying to form, that is less than 2 into 10 to the power 5. So you can run something in order of n. Now, how do you solve it still? Because the brute force approach would be try all n factorial combinations and check for the condition. Obviously, that would not work. So let's analyze the condition. What the condition is, that you should, for any same value, for any two different I and j, they should differ by an even distance. What do you mean by that? If you take any string, okay, let's take the indices. Okay, so in this string you would have some values at these index. Okay, let's try to analyze any one of the character. Let's say if you're trying to analyze about A, because your condition is both I and j should have the same value. So either they would have the same value a or b or c. There are only 26 options of the same value that they can have. So let's analyze all these 26 values differently. Let's say for a, let's say the frequency of a was 3. So you may have a here, a here, a here, let's say at 1 3 4. Now would this placement satisfy our condition? How do you check that? So the check is basically, if you pick any two of the positions, they should differ by an even distance. What do you mean by that? When would two values differ by an even distance? So differing by an even distance, 1 and 3 differ by an even distance, 1 and 5 differ by an even distance, 1 and 7 differ by an even distance. Or if you take 3, then 3 and 5, 3 and 7, 3 and 9, 3 and 1. So you can see, if you take any two odd values, their difference would be even. If you take any two even values, 2 4, 2 6, 4 6, their difference would be even. So writing I minus j mod 2 equal to 0 is same as saying that I modulo 2 minus j modulo 2, whatever is the absolute value of that, that should be 0. That is I modulo 2 should be equal to j modulo 2. This condition is that modulo 2 values of both I and j should be equal. That is, their parity should be equal. Basically, either both of them should be odd or both of them should be even. That's your condition. So your condition is that if you are picking this a, all the positions where you can place this a should either be even or all the positions should be odd. Even if there is one place, like you there are 4 a's you have, if you place 3 of the a's in odd positions and place one of the a's in an even position, then still it would become invalid. So whichever character you take, if you are taking a, place all the a's at even position or place all the a's at odd position. You cannot have a mix up of an even and odd positions for any particular character. Same for b, place all the b's at even position or place all the b's at odd position. That's your condition. Now, keeping this condition in mind, how do you satisfy it for all the 26 characters? You need to decide in how many ways basically you can satisfy the condition. So what would be the number of ways? Let's see how many even and how many odd characters you have. So if you have an string of size n, so if let's say n is 5, so you would have 3 odd positions and 2 even positions. So odd positions would be 3, even positions would be 2. And if you have one even n is 6, then for that 1 2 3 4 5 6, number of odd positions would be 3 and even positions would also be 3. So odd would be 3, even would be 3. So for any n, you can say number of odd positions is n by 2, number of even positions is, you can say, the seal of n by 2, even positions is the floor of n by 2. These are the number of odd and even positions. So now you need to, for all the 26 characters that you have, a b c d up till z, you are given the frequency in array C, you are given some frequency of all these characters. So what you can do is, if you're assign every character either even or odd, assign every character a position. Let's say a is assigned even, b is assigned odd, c is assigned even. Okay, c doesn't exist if its frequency is 0. You can either ignore it or assign it anything, it doesn't matter. About d, you can assign it, let's say, odd. Okay, let's say all the remaining values were 0. So the condition is the sum of the odd frequencies should be this, the sum of the even frequencies should be this. Keeping this thing constant, if you can keep this thing constant, then what are the different assignments that you can give? Okay, if you can find that number of ways. Okay, so what are the number of assignments? What assignment I'm talking about? Or assigning all the 26 characters either even or odd. So let's say the number of assignments is X. First of all, how would you compute this assignments? You can use a DP for that. You can clearly see this is like a knapsack DP. So you have these 26 values, uh, the frequency of all these 26 values. You need to select among these. Every index has two choices. Either, let's say you are trying to just try to select some values that sum up to odd, sum up to this n by 2, let's say. Okay, so you would place those values at odd position, remaining values would automatically come to even. So try to compute for one of them. Let's say I'm trying to compute for odd positions. What are the number of valid assignments, so that the sum of the frequencies of those values whom I'm assigning odd is n by 2. So that can easily be computed. For every index you have two choices, either select it or don't select it. So that way, through a knapsack DP, a DP of the DP, here what DP you would have? The sum. So the size of the DP would be n. So if you want to form a size of, let's say, x, and the second state would be I, so up till index I, can you form a sum of x? So this I'm telling as x. So this DP state is number of ways to form sum x using values from 0 till index I. So this is your DP state. Your DP state is number of ways to form a sum x using only values up till index I, and your transition would be very simple. DPXI is either you select the ith index. So if you don't select the ith index, then you would search for sum x in till I minus 1, or if you select the ith index, then you would search for x minus ci till I minus 1. So this would be your DP transition, and this is your DP state. So this way, obviously, you can, after computing this DP, the number of assignments that I was talking about, the number of assignments that I was talking about, that would be the DP of, if you go up till the whole index I, and you need to assign a sum of n by 2 up till index would be 26. Okay, just go to all the values up till index I, up till index 26 for all the 26 characters, and select some values to form a sum of exactly n by 2. So in order to form a sum of exactly n by 2 using all the 26 characters, whatever is the number of ways, let's say this number of ways is something y. What should be your final answer? Now for every assignment, let's say you pick one particular assignment. Okay, one particular assignment is, let's say for this was one particular assignment. A is assigned even, B is assigned odd, D is assigned odd. So here you have 3 plus 2 plus 1, 6. So you have 6 positions. Out of them, in all even positions, you need to keep A's. Okay, so in the 3 even positions, you would keep A's. In the odd positions, you can keep 2 of the odd positions would be occupied by B, 1 of the odd position would be occupied by D. So either you can keep BBD, or you may keep DBB, or you may keep BDB. So there would be 3 ways. So for one particular assignment, you are getting 3 ways. So what is this number of ways? So your answer would be finally the number of assignment that you get y multiplied by number of ways for each assignment. So what is the number of ways that you can form different strings for each assignment? So the number of ways would be all those values that are assigned odd. Okay, let's say B is assigned odd, D is assigned odd. So there would be this many positions that are assigned odd. First of all, you can permute through all these many positions. So factorial of that would be the number of ways to permute through all these positions. But out of them, let's say here it was you are computing for A. So all the 3 positions are A. So you would not have 3 factorial is equal to 6, but rather you would have only 1, because all the 3 values are same. So you have to divide by 3 factorial. So you know the number of permutations for to permute n values where a values are same. So number of ways to permute n values where some group, some x1 values are same, x2 values are same, x3 values are same. That is n factorial divided by x1 factorial, x2 factorial, x3 factorial. If you know this from PNC, then that's what you need to do. So your final answer is going to be this y multiplied by what's the number of ways. So first of all, number of odd positions are n by 2 seal. Factorial of that, number of ways to permute among them. N by 2 floor is the number of even positions. Factorial of that divided by the number of groups that are same. So C1, whatever is the frequency of C1, factorial that, C2 factorial, C3 factorial, up till C26 factorial. Up till C26 factorial. So this would be your final answer. Is the logic fine? So this is permute among the odd positions, permute among the even positions, and then among those permutations there would be many common things because C1 values are the same. So there are like 3 A's which are same, so divide by 3 factorial. There are 2 B's which are same, so divide by 2 factorial. This way you would get your final answer. So for this particular assignment, your final answer would be, so this n by 2 is 3 factorial, that n by 2 is also 3 factorial, divided by 3 factorial, 2 factorial, 1 factorial. So this would be, so 3 factorial, 3 factorial cut, 3 factorial by 2 factorial, 3. So I hope you got, for this there were 3 ways, you got a 3, and this multiplied by the number of assignments that you got, okay, that you computed through DP. So I hope you got how we are going to compute this. Time complexity for computing the DP would be order of n into 26. In order of n into 26, we would compute the DP. And well, if you can pre-compute the factorials mod m, pre-compute the factorial mod m till whatever 5v5 is given. So in order of 5v5, you can pre-compute the factorials mod n. Then you can compute this product divided by this in, you can pre-compute the inverse factorials as well. So after that, this multiplied by factorial this, inverse factorial this, inverse factorial this, modulo m you can do in order of, basically this would be order of 1 time, this would be order of 26. So order of 26 time would be taken to compute this, order of n into 26 time would be taken to compute this DP. So in overall n into 26 time we are computing the whole thing. So if the logic is clear, I think we can move to the code. Is it now clearer, Harsh? If it's getting confusing, maybe you can write which part it's getting confusing, then I may explain that part. Otherwise, if the whole thing is not clear, then maybe you can go back and rewatch it. Okay, so I think it's clear, so we can move to the code now. Basic concept was, the condition given is, so I'll just reiterate what we did overall in the problem. So the condition given to us, what the problem was saying, this condition basically reduces to that both I and j should have the same parity, either both of them should be odd or both of them should be even. That means if I pick any character, let's say I pick this character A, the two places where this A is placed, all of them should either belong to odd positions or even positions. That's the conclusion we got from the given condition. After that conclusion, we can say that for odd positions, basically you need to divide these frequencies. So every character would either receive odd position or even position, odd position or even position. Likewise, every character from A to Z would receive an either an odd and even position, and this distribution should be such that the sum of frequencies of odd positions should be equal to n by 2 seal, and sum of frequencies of even positions should be equal to n by 2 float, because these are the number of odd positions we have, these are the number of even positions we have. And to ensure this, we can use a knapsack dp to compute this, where dp xi denotes that up till index I can we select some values so that the sum of the values is x. So those selected values I'm saying belong to the odd position, unselected values belong to even position. So through a knapsack dp we are computing the number of ways to get this assignment. If the number of ways of getting this assignment is y, then my final answer is, for every assignment inside that assignment also we can have different ways to form a string. So to explain that number of ways, if we have a b c where a is 3 2 1, and here if we have assignment of odd even, then for that assignment either I can, in odd positions I can place a, and in even positions I can place bbc like this, or bcb, or cbb. So there were 3 ways. So the number of ways is computed as number of odd positions are n by 2. Okay, the number of odd positions factorial of that, number of even positions factorial of that, divided by the number of same values. So there are c1 a's, so factorial of that, there are c2 b's factorial of that way c26 factorial. So this is the number of ways to permute through one particular combination. And through dp the y combinations that we computed through dp, multiply that y to get your final answer. Okay, I hope the logic is clear now. We can move to the code. So if we analyze the code, what I said exactly that is done. Take the input, all the 26 values of c in a vector of size 26, size 27, so that I have indexes from 1 to 26. In n I accumulate c, so the sum of ci is the size of the string that I would have, which is my n. Then I take a dp of 26 cross n. Okay, so 26 so that I have indexes from 1 to n, 27 so that I have indexes from 1 to 26. So here the dp I was showing was I was taking dp xi, like in the code I have taken dp ix. Okay, just the indexes are swapped left, right? So I taken first, x taken afterwards. I hope that doesn't create a confusion. So these are the indexes of all the characters through which I would be iterating. These are the sum that I need to check, that I need to make sure that I get a sum of n by 2. So my base case would be I equal to 0. That means I have taken nothing. And if I have taken nothing and I get a sum of 0, that is one way. Taking nothing would give me a sum of 0. For all the remaining sum, the number of ways is 0. So I've initialized this dp with 0. So there is 0 number of ways for all the remaining sum with 0 values, and for 0 sum there is one way. So this is the base condition. So for I from 1 to 26, j from 0 to n by 2, we only need to compute till n by 2, because in my final answer number of ways is dp 26 n by 2. So computing till n was not required, although you may compute till n also, no issues. Then your transition is basically dp ij is dp I minus 1 j plus dp I minus 1 j minus ci. Now in order to add this thing, you need to check whether this j minus ci is positive. Otherwise, if this is negative, you may get index out of 1, a negative index error. So just check if this thing is positive. Also check that ci is greater than 0. If the ci is same as 0, then j minus ci and this j, both of them are the same. So basically you are adding the same thing 2 times. So this would give you a wrong answer. You would be computing too many times. So if ci is 0, that means it is neither going to odd nor going to even. So just move forward with it. Continue your loop forward, dp ij as dp I minus 1j. But if this is greater than 0 and this is positive, then only add this term. So this is my transition. I keep taking mod m whenever I do any addition or any operation. Final answer would be dp through dp, whatever the number of basically ways that I computed in order to arrange them. And for each arrangement, the number of permutations we have is factorial n by 2, factorial, this was floor of n by 2, this was factorial ceil of n by 2. I have pre-computed my factorials. So in fact compute function, I've pre-computed factorials and inverse factorials already. Like I'm not using inverse factorial in the code. You may use inverse factorial, it would be better. After multiplying the numerators, I need to divide by the denominator, the product of these factorials. So for that, I'm using modulo inverse function, that answer divided by factorial of ci. I'm running through every I. So I'm just dividing by ci factorial. Okay. I could have written multiplied by inverse factorial of ci. That would be like here I'm using extra log n complexity, so that was not required. So, but still okay. That extra log n doesn't matter because it's 26 into log n. That's not my upper limit. My main limit would be 26 into n. So if I analyze the time complexity, this is input part. This is taking 26 into n time. So this is 26 into n. This is order of 1, and this I'm running 26 times. This is taking log n time. So this is 26 into log of whatever, log of, I would say, let's say 1e6, because this ci may go up till 1e6 or 5e5. This may go up till 5e5. Okay. Or ci, I should write. Okay. So this is the complexity for this part, but overall this is the upper limit for me. N would be greater obviously. So my overall time complexity would be order of 26n, and my space complexity would be, I'm using a dp of 26 into n. That's the upper thing. Rest all are normal variables. So order of 26 into n, space complexity as well. I hope this problem is clear. If there is any doubt, please write in the chat so that I can clear it before moving on to the next problem. Yeah, 2 to the power 26 is, I think, about 1e7, so that may work, but I don't know what is your logic for 2 to the power 26 solution. But yeah, if the overall complexity is exactly 2 to the power 26, that's about 1e7, it would work. Any more doubts in this problem, or should we move to the next problem? Okay, so I think we can move to the next problem now. Okay, so next we have problem E, which is zebra-like numbers. We call a positive integer zebra-like if its binary representation has alternating bits up to the most significant bit, and the least significant bit is equal to 1. For example, 1521, their binary representation is 1, 101, 10101. So up till the least significant bit, if you write the number in binary, it would be of the form 101010. Then it is called a zebra-like number. Now 01 or 0101, that is not a zebra-like number. So the least significant one should be 1, not this. Okay, so that is clear. Now we defined the zebra value of a positive integer e as the minimum integer p, such that e can be expressed as the sum of p zebra-like numbers, possibly the same, possibly different. So the zebra value of any positive integer e is the minimum number of minimum integer p, so that e can be expressed as the sum of p zebra-like numbers. So if you can use p zebra-like numbers to represent the number e, then you can say that the zebra value of integer e is p. So the minimum p with in which you can do this. Given three integers L, R, and K, calculate the number of integers x such that x is in the range from L to R and the zebra value of x is equal to K. So basically, constraints are LR up till 10 to the power 18, K up till 10 to the power 18. So basically, you are given some random two values L and R. You need to check in between that range from L to R how many such numbers x exist whose zebra value is K. So you are given L, R, and K. How many numbers in the range L to R having zebra value K is what you need to answer. So let's leave the test cases and understand the problem. Okay. So you are given L, R, and K as input. What you need to answer is in the range L to R, how many numbers have zebra value equal to K. Now, what is zebra value? Zebra value of any number x is defined as, let's say, zebra value of x is the minimum p so that x can be represented as sum of p different zebra numbers. So where zebra numbers are 1, 101, I'm writing in binary 10101, 10, 10101, so 10. So these all numbers are the zebra numbers. So let's see what are these numbers in decimal. Okay. So in order to solve the problem, first let's understand some patterns and try to analyze what this zebra value is, and through some examples try to think what is the zebra value of a number, how to compute the zebra value of a number. If you can find a way to compute the zebra value of any number x, then we would think that how can we find numbers having zebra value k. So first let's try to find how can we compute whether what is the zebra value of any given number x. So what are the zebra numbers? This is 1. This in binary is, okay, like if you analyze what is this in binary, so this is 1 plus this value, this has a value of 4 because 0, 1, 2, so 2 to the power 2 is 4. So this is 1 plus 4 equal to 5. What is this? This is 1 plus 4 plus 16. Okay, so this is actually 1 plus 4 plus 16, which is 21. This is 1 plus 4 plus 16 plus 64. So 1 plus 4 plus 16 plus 64, which is 85. Likewise, we have the numbers. So what is a zebra number? First of all, a zebra number is all the odd, like if you look at any number. So let's say any zebra number. After that, if you have zeros, so this is a zebra number. Then for any zebra number, you would have, okay, start with 0. This is 2 to the power 0. This is 2 to the power 1, 2 to the power 2, 2 to the power 3. These are the values of these indices. I hope you know in binary. So basically, a zebra number is 2 to the power 0 plus 2 to the power 2 plus 2 to the power 4 plus 2 to the power 6. Likewise, so any zebra number is 2 to the power 0, 2, 4 up till some 2 to the power x. This is any zebra number. So first of all, how many such zebra numbers would exist? For the given range of L and R up till 10 to the power 18. So till 10 to the power 18, how many zebra numbers would be there? So 2 to the power 0 would be 1, 2 to the power 0 plus this would be the second, this would be third, this would be fourth, this would be the xth zebra number, not xth zebra number. 2 to the power x is going to be, or I should write 2x. Okay, I have to move in the powers of. So this is 2 into 0, 2 into 1, 2 into 2, 2 into 3. So 2 to the power 2x would be the x plus 1th zebra number. So what is the maximum zebra number that you would have, such that 2 to the power x is less than equal to 10 to the power 18? Once it exceeds 10 to the power 18, then it's done. So basically 2x should be of the order of log of 10 to the power 18, log base 2 10 to the power 18, which is approx 60. So x should be about 30. Okay, so if you go up till 2 to the power 2x, basically 2 to the power 2 into 30, so 2 to the power 60 would exceed 118. So x would go up till 30. So from 0 to 30, a total of 31 numbers are there. So at max, like, you would have 30 zebra numbers. What exactly are those 30 zebra numbers? These are 1, 5, 21, 85. Then you would have 85 plus what is after 64. 64 is 2 to the power 6. Then you would have 2 to the power 8, which is like 256. So 256 plus 85, you would get 341. So if you notice the pattern, this way we would move on, and the 30th number would exceed 118. So we have only 30 zebra numbers. And how do we compute the minimum number of zebra numbers required to form any integer x? Okay, so zebra value of any integer x. So using these integers 1, 5, 21, 85, 341, we need to form the x using minimum amount of these numbers. So let's say, okay, so the zebra numbers we have is 1, 5, 21, 85, and then what we computed here is 341, 341, and so on. So using these zebra numbers, you need to form. Let's say I need to find the zebra value of 7. How can I form 7? I can form 7 using 5 plus 1 plus 1. This is one way. Or I can form 7 using 1 plus 1 plus 7 times 1. So this 7 times 1 would take 7 zebra numbers. This way I am taking only 3 zebra numbers. So this is the minimum. So for 7, my zebra value would be 3. Obviously, I cannot use something greater than 7 like 21 or 85 here to form a 7. So the best I could do with minimum amount of numbers is 5 plus 1 plus 1. Let's see, like, what can we do for 20. So 20 we can form using 5 plus 5 plus 5 plus 5, 4 times 5. Now obviously we cannot use a 21 to form a 20, so I can only use 1 and 5. So use 5 times 5, 4 times 5 to get 20. That's the best way in 4. If I'm using 1, then I'll have to use 20 times 1, or maybe 3 times 5 and 5 times 1. That would obviously be greater. Let's say I want to form something like 18. What's the best way to form 18? So 18 can be formed only using 1 and 5. So take 5 plus 5 plus 5 3 times, you get 15, and then 1 plus 1 plus 1. Because after 15, if you again take a 5, you would reach 20. You cannot exceed that. And if you take less number of 5s, if you're taking only 2 5s, then you will require 8 number of 1s. That would have total 10. But here you had only 6 numbers. So for below 21, best thing was, for 5, use a 5, rest 1. From 5 to 9, use a 5 and rest with 1. From 10 to 14, use 2 times 5 and rest value with 1. From 15 to 19, use 3 times 5, rest value with 1. For 20, use 4 times 5. Now for 21, obviously this is already a zebra number, so you would use just 21 and do it in one time. Zebra value of any zebra number would be 1. That's quite clear. What about 22? Use 21 plus 1. 23, you can use 21 plus 1 plus 1. 24, you can use 21 plus 1 plus 1 plus 1. 26, you would use 21 plus 5. Before that, 25 would be 21 plus 4 times 1. So for these values here, you would use 2 values, 3 values, 4 values, 5 values. Here again 2 values. Another way to form, like here, why are we always using 21? Maybe there is a way without 21 we can do it with less numbers. So let's check. Let's say for 24, if I'm only using 5, then 4 times 5 plus 4 times 1 would be 8 numbers. So 4 is obviously less. It's better. For 25, I can form 25 using 5 times 5. That would also require 5 numbers. And in this case also, I'm requiring 5 numbers. So for this particular way of case, I have two ways. Either I can use 21 and 4 times 1, or I can use 5 times 5. But this is the only edge case. For that also, it's giving the same value. In both ways, you are getting 5 numbers which are making it 25. So basically, if you assume that this 5 times 5 way doesn't exist, still through this way, I can make using just 5 numbers. So my answer is still okay. So I can basically assume that for any number x, whichever is the first zebra number just less than x. So for 25, it was 21 was the first zebra number just less than x. You'd always use that zebra number as many times as you can. After that, so for 25, you can use 1 time 21, and then whatever 4 is remaining. For that 4, again, you basically recursively call the same thing. For 4, again, check whichever is the zebra number just less than equal to 4. That was 1, so use 4 times 1. If it was 27, then zebra number just below 27 is 21, so use 21. Remaining we have 6. Zebra number just below 6 is 5, use a 5. Remaining we have 1. Just below 1 is 1, use a 1. So this way in 3 numbers you can form. Let's say something like 43. Just below 43 we have the zebra number just below 43 is 21, because after 21 we have 85. So for 43 we can use 21 plus 21, 2 times it can be used to form 42, and then we are left with 1. So add a plus 1. So in 3, just using 3 numbers we formed it. And if it was 41, then you, after using 1 time 21, you are left with 20. You cannot use another 21. For 20, just below 20, which is the first zebra number, it is 5. So add 5 how many times? You can use it 4 times to get 20. And this way you required 5 numbers, 1 year and 4 year. So I hope you understood. So this was through intuition and through analysis that yes, you are getting the feeling that yes, this process is working. Is there some proof that always this would work? So I'll give you a small proof for that. What are the zebra numbers that I'm having? It's 1, then we have 5, then we have 21, then 85. Can you observe some pattern here? After 1, 5 is 4 times 1 plus 1. 21 is 4 times 5 plus 1. 21. 4 times 21 plus 1, 85. 4 times 85 plus 1, 341. So basically always the next number is into 4 plus 1. That is clear. Now let's assume for, if we want to find the zebra value of any number x, let's assume for this x, the zebra number just below x is y. Okay, so y is the zebra number just below x. Now my say is I would always use a y here to reduce this x. So what I'm saying, what I'm trying to prove is zebra number of x is zebra number of x minus y. Okay, so always reduce this x by y, and in this process using a y, I used 1, basically one one zebra number I used. So use a y, and the remaining sum that I need to obtain is x minus y. So again run a recursive function on x minus y and plus 1 that I said. So I'm telling to compute the zebra value of any number x. This is the recursive function, that whichever is the first the greatest zebra number below x. So just below x, whichever is the greatest zebra number, use that value once and recursively call the function again. So keep doing that. Keep doing that. Whenever you have, let's say, x equal to 26, zebra number below that is 21, use it. Then for 5, below 5 is 5, use it. Keep doing that. What is the proof that this process would always be optimal? The proof is, let's assume this is not optimal. So let's assume that the zebra number of x doesn't involve computing using a y. So like for something like x equal to 27, if it was 21, if I'm telling that it doesn't involve using 21, then at max what I can do is I can use 5s. Okay, so whichever was the way where I was using 21, I would have to replace that 121 with 4 5s and a 1, or replace it with maybe 3 5s and use that 6 along with the remaining 6 to get some different number. But that would never be optimal, because if I'm using 5 there, in order to replace that 21, I would have to use this 5 4 times, and still I would have been left with 1. So whatever remainder I have here, let's say the remainder left is 6, then if I'm not using 21, if I'm using only 5, then I can increase this remainder to by 16. If I only use 5, then I'll be left with 16 extra that I can utilize. So maybe not using 21 and using 5, the only benefit would be to add this 16 to 6 to get some 22, which can be done in lesser number of ways as compared to what 6 can be done in. But this is never possible, because okay, like for the exact proof, because just below 21 the previous number, just below x the previous number is actually x by 4 or x minus 1 by 4. So if you are using x minus 1 by 4, that this 16 that I was telling is x minus 1 by 4, which is 4x minus x is 3x plus 1 by 4. And adding this to any of the remainders, okay, this remainder is greater than equal to 1. Any of the remainder, if this remainder is greater than equal to 5, then obviously I can use a 21. And if it is less than 5, then like it would involve more number of ways. Okay, I hope you have understood through the intuition. Basically the main proof was that you would at max use a number 4 times. If you are using any number 5 times, if you are using any x 5 times, like if you are using a 5 times, then forming a 25 is same as using 21 and 4 times 1. So this thing is equivalent, and using anything 6 times is never optimal, because 30 can be formed with 21 plus a 5 and then 4 times 1. So always like using it more than 4 times is never optimal. So I hope you would have got the intuition behind it. So let's skip ahead. Okay, so once you know this thing, that for any number to compute the zebra value, my function is whichever is the greatest zebra number just below it, subtract that value first, keep subtracting that value. Now if there is if the value reduces it below y, then there you would form a new y, keep subtracting like this. Now once you know this formula, how do you compute your actual question? So in your actual question, you have to compute for a range from L to R, what all numbers have a zebra value of x, k. What all number have a zebra value of k? So first of all, in order to compute for the range L to R, main reduction is I can compute the function. I can say I am computing a function x comma k. So this function that my function that from L to R numbers having zebra value k is same as instead of taking this function, let's say this was function g, I take a function f x comma k, where this function is how many values from 1 to x have a zebra value of k. Okay, so then my final, this would be f of rk minus f of l minus 1k. So this I hope you know. So I'm going to compute from 1 to x, okay, because it's easier to compute all numbers less than equal to x. So I'm going to compute, my function would be how many numbers less than equal to x have a zebra value of k. Then for the range from L to R, I can compute numbers less than equal to R subtracted by numbers less than equal to L minus 1. This way I would get my required answer. So let's try to compute these functions. How many numbers less than equal to x have zebra value equal to k? Now, this recursive function can be in turn written as, so for all the numbers, let's say x is something like, first of all, for the first conclusion, okay, we'll come to that later. Let's say what recursive function can we write from this. For this function, I'm telling from 1 to x, how many numbers have zebra value k? Let's say x is something like 27. From 1 to 27, how many numbers have a zebra value 3 if I'm trying to compute? So for all the numbers from 1, if I'm trying to compute from 1 to 27, below 27, 21 is the zebra number just below 27. So from 22 to 27, for all these numbers, the first number that you would choose would be 21. First, you would subtract them by 21, and then after subtracting them by 21, 22 to 20, or I can say from 21 to 27 only. From 21 to 27, for all these numbers, if I want to check whether their zebra value is equal to k, then I would have to check whether the zebra value of, because for all these numbers, I would always use 21, whether this minus 21 would give me a range of 0 to 6. 21 corresponds, 21 minus 21 is 0, 27 minus 21 is 6. So basically, recursively, I can check from 0 to 6. If these numbers want to have a zebra value of k, then these numbers should have a zebra value of k minus 1. Then only these numbers can have a zebra value of k. So I can say for x equal to 27, this can be divided into 1 to 20 and 21 to 27. These are the two ranges. This can in turn be written as, f of, I have to compute from 21 to 27, this reduced to 0 to 6. So it is f of 6, but k got reduced by 1. So this function can be written as from 21 to 27, if I want to have a zebra value of k, then from 0 to 6, I should have a zebra value of k minus 1. And this can be recursively written as f of same 20 with same value k. So I can say that this f of 27 comma k, f of 27 comma k is f of 20 comma k plus f of 6 comma k. Number of values having zebra value k from 1 to 20 is this. Number of values having zebra value k from this to this is this. So basically my recursive function is f of x comma k is, if I compute a y which is just less than equal to x and this is a zebra number, then I can write this is f of, either I would leave it till y minus 1. So from 0 to y minus 1 having zebra value k, okay, this thing, or from y to x, so from y up till x having zebra value k minus 1. So this is x minus y is 6. So f of x subtracted by y, zebra value k minus 1. So this is my recursive function that I'm saying. Now, what if I implement this recursive function? what complexity would it have? So in a naive way, if you think, what should be its complexity? Its complexity should be like this x may vary from 1 to 10 to the power 18. This k in the given constraint was up till 10 to the power 18. So even if you apply a dp for dp of x comma k, that would be 10 to the power 18 into 10 to the power 18. This won't be accepted. Okay. So like if you are writing a dp state like this, you cannot create a dp of 10 to the power 18 cross 10 to the power 18. But if you just write a recursive function like this, then this would not take too many states. Why? Let's try to prove that. First of all, let's look at this k. Okay, let's forget about this x. This x may vary. This first state may vary. Like you're writing y minus 1, then this 2 2 2. Like if you form the recursion tree, one would give rise to two values, this would give rise to two values. This may go exponential. Even if your x is okay, whatever, even if this y can be only 30 values, still this thing may go exponential. But we'll see whether it is going exponential or not. But first, let's look at this k. What can be the maximum like value of any, what can be the maximum zebra value of a number x? Okay, this k should be the number x should have a zebra value of k. What can be the maximum zebra value of any number x? The property of finding the zebra value x that I explained, that you would find the greatest zebra number just below x, subtract that. At max, any zebra number would be taken how many times? You have at max 30 zebra numbers. Okay, so from 1, 5, 21, 85. At max there are 30 zebra numbers, and in your final sum making x, you would select this one maybe two times, this 5 one time, 21 one time, like that. At max, any zebra number would be taken four times. From the proof of that at max you would take any zebra number four times. So at max, how many zebra numbers can you take at a time? Is if you take this four times, this four times, this four times, this four times, and the last zebra number also four times. So at max you would have 30 into 4, 120 zebra numbers. You would never have more than 120 you would never have more than 120 zebra numbers used to form a number. You can always form any number up till 10 to the power 18 using less than or equal to 120 zebra numbers. So the upper bound on my k is 120. So I can directly say if my k is greater than 120, my answer is 0. That there are no numbers having zebra value equal to k, which is greater than 120, because all values can be formed using less than 120 zebra numbers. So all the values would have a zebra value less than 120. So this is the first proof. So I have reduced my range of k. Whenever k is greater than 120, just answer directly 0. So now my range of k is reduced very much. Instead of 10 to the power 18, I have only 120. Okay. Now this is reduced very much. But still this x can vary up till 10 to the power 18. You cannot use a 10 to the power 18 cross 120 dp still. So let's see this recursion. Now in this recursion, if you notice, for any random x, okay, if you notice the recursion tree of any random x comma k, you have x comma k. From that you would write f of y minus 1 comma k, f of x minus y comma k minus 1. First of, and then from this again you would form 2, from this you would form 2. Okay, it may look that it is going exponential, but if you notice, this thing that you are writing, whenever you are writing y minus 1k, so if I'm writing this as a like different type of function, so this is a special value. Y minus 1 is a special value. At max, how many y minus 1 can exist? At max you can have 30 different y's, 30 different zebra number. So at max there are 30 different y minus 1 only. So this type of function, so this is expanding into different a lot of values, but this is not going exponential. From 1 you would have 2, then you would have 4, 8. It's not like that. Some of them would coincide because this type of function f of y minus 1k, at max this can be 30 and this can be 120. So at max there can be 120 into 30 different this function. So basically you can use a dp to, if there is some repetition in your recursion, you can use not a fixed dp or by creating a dp of size 118, you can use a map type dp, so that whenever you have a y minus 1, for those special values you are mapping that y minus 1 comma k to one particular value. So this recursion tree that you are drawing, whatever this left side that you are getting, that won't be exponential, that would be a straight line. So for any f of x comma k, so for f any x comma k, you would have, basically you can say, or let's say you have a f of y minus 1 comma k and f of x minus y comma k minus 2. Okay, this would again reduce to one f of whatever this value was. There is would be some y dash just below it. So some y dash minus 1 comma k and f of whatever was that y dash minus y dash k minus 2. Okay, this would give rise to, okay, now this would again give rise to this y dash minus 1. Now this is a special function. Okay, this is a special function. What about this? This would again give rise to some f of y double dash minus 1 comma k and a function f of x minus y dash minus y double dash comma k minus 2. So if you notice this recursion tree, then this thing is rising from k minus 1, k minus 2. Here I would have k minus 3. So this would at max vary, this k would reach 0. So this k would reach 0, and I can say this thing would at max be, k can be 120. So at max 120 function calls of these random function calls. So at max 120 random function calls, and rest of the function calls would be on special values. Okay, so the number of special function calls would be, let's say the special function calls of any y minus 1 comma k, this is a special function call. At max this would be 30 into 120. So 30 into 120 special function calls, and these random with some random values of x, those function calls with some random values of x, okay, x comma k, that would be at max, you can say, for this, for one particular tree, for one particular, like if you're computing one particular special function, this would be at max 120 for one function call. Now for all these special function call, inside that also you would have one random function call inside any of the special function call. So inside this also you may have some 120 random function calls. Overall time complexity would still remain 30 into 120 into 120. Like this is a very big upper bound to it. Okay, so this is like 3 this is about 3 7, but this is still, I'm taking a very higher upper bound. The actual upper bound is very less than this. because there would be a lot of collisions and all. So this, I'm assuming a very high upper bound. So through a very high upper bound, I'm calculating 3 7 states, but it would be still very less than this. At max, maybe 1 is 6 states only. Okay. So your overall time complexity would be, whenever you compute a state, store that in a map DP. So DP of, you would have DP of x comma k, but this would be like a map. Okay, this k can be only till 120, so this can be a vector, but this x would be a map. Okay, so that you can have random values of x from 1 to 10 to the power 18. But at max there would be very less number of values. So here, even if you have like 1e7 values I'm taking, and then using a map would have an extra some log complexity. Overall, that is still fine. Overall, it won't exceed 1e8 complexity. Okay, because this is a very high upper bound of 3 7. Actually, it would be like at max 1e6 1e5 only. That multiplied by even extra log n would be okay to go with. So you can implement this recursion with a map type DP memoization to reuse the repeated states to get this in the correct time complexity, and this code would be accepted. So I hope this logic is clear. Now what you need to write is basically just this recursion. That's the only recursion you need to write. Okay, is there any doubts in this problem? Okay, so I hope the solution is clear. If you have a doubt, you may write. Okay, if it's off topic, then after the code at the end you may ask. Okay, no issues. Is there any doubt regarding this problem, or we can move to the code part now? So let's move to the code. So the code is quite simple. You need to just write this recursion. Okay, you also need to focus on the base cases also. You also need to write the base cases. What base cases should we have? So whenever we call f, okay, one base case would be when k reaches 0. So f of any x comma 0, okay, when k is 0, what answer should you give? So k0 basically means that numbers having that if you don't add any zebra number, what sum can you get? So zebra, I can say that the zebra value of 0 is 0, because 0 is such a number which can be formed without the use of any numbers. If you don't add any numbers, you would get 0. So the zebra value of 0 is 0. So whenever you have k equal to 0, then f of x comma 0, in that I'm saying I'm computing from 0 to x, in the range from 0 to x for all the values. How many values have a zebra number? K. So from 0 to x, only 0 would have a zebra number of zebra value of k. So for k equal to 0, I would return 1. That 0 is the number which has a zebra value of 0. Now, initial definition I was writing from 1 to x. Why I have considered 0? Because let's say some x is 21. Then from that, when I write the recursion of x minus y, it would be f of 21 minus 21. I would call f of 0 comma, and let's say k was 1. So I can form 21 using one number which is 21, but this in my recursion it would result in f of 0 comma 0. So if I get to f of 0 comma 0, then I should return 1. So with that logic in mind, if I subtract 21 and get some 0, or even if it is 22, okay, then if I subtract 21, I'm computing for it in 1 to 22, there would be a 21. So for that 21, when subtracted by 21, would result in 0. So you need to consider that 0 as well in your base case. So for k equal to 0, I would return 1. I hope you understood why the zebra value of 0 is 0 for the base case. So for k equal to 0, I return 1. That is one base case. And another base case is for x equal to 0. So when x reaches 0, if k is 0, then I've already returned 1. Otherwise, to form any number from 0 to 0, it should have a zebra value of 0. So if it has had any other zebra value, I should return 0 as my answer. That there are no numbers having zebra value 0. So my base conditions are, if k is 0, return 1. If k is not 0 and still x is 0, then return 0. So these two base conditions are written. After that, my this recursion is going to just compute everything. So do this memoization. For memoization, I have used the map of array. So like this would be a 2D DP of x comma k, but I'm using an array of map. So I'm writing dp of k comma x here. So dp of k is an array and this x is a map. So I'm using a vector of map or a array of map. So this mx is taking 120. So I've created an array of 120 maps. Okay. So dp0 represents my map for k equal to 0. So dp0 represents my map for k equal to 0. So in this map, if I'm writing 1 corresponds to 2, that means dp01 is equal to 2. That's what it means. Okay. So I've taken a map of array. Now for memoization, I just do in dpk. If I find x, return dpkx. That's what my dp value is. Otherwise, compute it. And finally, I would, whatever answer I compute, I would store it in dpkx. Okay. So how do I compute the answer? First, I would form those 30 zebra numbers. So I pre-compute those 30 zebra numbers. I start with x equal to 1. Every next number is 4x plus 1. So in a global vector vec, I just push back all those values. Start with x equal to 1, push back 1. Then 4 into 1 plus 1 would be 5, push back 5. 4 into 5 plus 1 would be 21, push back 21. So till x is less than equal to 118, I push back all the zebra numbers below 118. After that, so in vec, I have in serial order, in sorted order, all the numbers from 1 to all the zebra numbers. So in that vec, I can use an upper bound to compute. Previous of upper bound is going to give me the value just less than equal to x. Okay. The which is the first y just less than equal to x that I'm going to compute through this upper bound function. Once I get this y, my answer is just func of y minus 1k plus func of x minus y k minus 1. So as I had written my recursive function, y minus 1k x minus y k minus 1. So I call the same recursive function. This is my answer. I store that in my dp and return. So I've computed this function. Okay. And before going to the test cases only, I initialized my dp. I cleared all the values of my dp and initialized this vector, so that even inside like I have 100 test cases. So if inside the test case if I'm initializing that, I would get an into 100 extra complexity. But if I'm initializing outside only, then even if in some other test case I'd use the same function, then that would not change. My function is the same for any test case. The function doesn't depend on L, R, and K. Okay. So that's why I can initialize those things outside my test cases, and inside the test case, I'm just taking the input of L, R, and K. If K is greater than MX was 120. If K is greater than 120, I return 0. Otherwise, my answer is func of RK minus L minus 1K. Okay. Total numbers in the range from 0 to R minus numbers in range from 0 to L minus 1. So I get the numbers in the range from L to R. That's my final answer. Okay, so I hope it is clear to you. Time complexity, it is approx, I would say 120 into, as I had written here, but this is still a loose upper bound. Okay, so from this recursion tree proof, I had proved it's 30 into 120 into 120. So I'm writing that here, but still it's a loose upper bound. It's less than that only. Okay. And about the space complexity, whatever was the time complexity, uh, in my DP, I would have that many states only. So this DP would have at max that many states. Okay. So I hope the problem is clear now. Is there any doubts in this problem? Then you may ask. Okay, or if there is any other random doubts also, you can ask. I think all the five problems are clear to you. If you have any other doubts, you may ask then before I would end the BCD. Okay. So you will be given an array in one operation. You have can swap any two integers in the array. Find minimum operations to make array non-decreasing. So basically okay, it's this problem. So like I'll tell you like in brief the logic for this problem. So like for any given random array, if you can swap any two integers, basically you can always sort the array. That's like one thing you know. And if you want to find the minimum operations to do that, then let's suppose you have sorted the array. So create a copy of the array, and let's say that copy is sorted. Now compare the original array with that copied array. What are the positions that you are changing? Now, if you look at the changes, then like if you have some array 1, 3, 2, and if you sort it and then look at the changes, then as I told in the permutation problem, it is similar to that. Here you have no change. Here there is 2 and 5. So like the changes would form a cycle here also. If you compute this 2 and 5 would be connected, then 3 would be with itself and 2 and 5. So basically you need to swap 2 and 5. So in every cycle, in order to form that, so for that cycle, getting that would be the size of that cycle. So basically the sum of sizes of the cycle would be the answer. I think probably that should be the answer. If you have the problem link, then maybe you can try, but the logic is similar to that permutation thing only for this problem. That uh, I remember that maybe I have solved a similar problem. That's why I'm not 100% sure that this would be the solution, but probably it would be like that only. Like permutation, you would have the number of cycles. Okay, you have tried. um, do you have the problem link? Then maybe you can share that link in the comment. I'll if I am able to solve the problem, I'll reply you the logic in the comment only. You can comment the problem link after the session is over. You can post the problem link in the comment. Okay, because it would be similar to that. Maybe I have solved a similar problem, but okay, now it would take time. I think would have to end the stream now. You can post it in the comment. Okay. Okay, you may share the invite. You may even DM me on LinkedIn or somewhere if you wish. Okay, still. Okay, I think we can end the live stream now if there is no more doubt from anybody else. Okay, so thank you very much for joining in. Goodbye.